Today we have Professor Yanıkoğlu from Sabancı University and she is going to present her interdisciplinary work with Cerrahpaşa Faculty of Medicine and TÜBİTAK on detecting COVID infection on computerized tomography images. It's a quite, unfortunately, very recent topic, but very interesting. And Berrin Yanıkoğlu received her Bachelor of Science degree from Boğaziçi University and then her PhD from US in Dartmouth College, and worked at Xerox and IBM Research Center until 2000. In 2000, she joined Sabancı University as a faculty member. She's also a director of Berrin Center of Excellence in Data Analytics. And let's welcome Berrin, and the floor is yours.
Thank you, Selim. Okay, so let's start. So this project came to us as a collaboration request in early April from Cerrahpaşa University and TÜBİTAK Meteorology Institute. And the project team is the Cerrahpaşa University, my PhD students, Sarah, who has done most of the job, Umut and Mehmet. So the problem is this: exact diagnosis of the COVID-19 infection depends on what we know as the PCR test. But the PCR test can take 6 hours, and more importantly, it gives high false negative results, especially early on in the infection. So that means it can skip detecting COVID-19 infections. On the other hand, COVID-19 can be observed in computerized tomography CT images. So this is good and can be considered as an alternative, but now the radiologist who's expert in evaluating the CTs, they may not be able to see the CT scan for a couple of hours, in which time the unobserved, unevaluated patients, potential patients in general, they are just walking around in the hospital and so on. And so this is a very high potential for virus spread. So Istanbul Cerrahpaşa University asked us to look into the problem and see whether we could develop a computer vision machine learning system that can automatically detect COVID-19 infection by automatically analyzing CT scans. If we can do this, then what can happen is in seconds, one can immediately alert the medical faculty, and then they can disinfect both the room and they can also isolate the patient. Okay, so everything now is deep learning. I'm sure even everyone, even in high schools, they know. So we can just throw some data at deep learning, but we also have to understand the problem always for best performance. So what does a CT scan look like, and what does the COVID infection look like? I'll start showing that. So the COVID infection, the images look like this. All right. Okay. So the images on the left look like this. They are the healthy lungs. The black area in the center of the abdomen, they are the lungs. And the parenchyma is the word that doctors use, show a special healthy normal pattern, while the lung shape significantly changes as we go from up, where the thorax CT start, down, so lungs start, and then you see more of the lungs and so on. And then at some point, again, the lung get out of the view. These things on the circled with the red ellipses, they show the signs, the pattern of COVID-19 infection. They typically occur, we are told, in the bottom part in these images of the lungs, and they sort of show some they show some kind of a smoky pattern. That's how I see it, but they call it broken glass pattern. Okay. So when this thing was requested, they also had another request, which is, can we deploy this in 1 month? So normally this don't take, the projects such as these take a lot longer than this, but roughly in 1 month, we developed this system that I'm going to be talking about today. And then we are going to keep developing it as the project goes on. Okay, so what is a computed or computerized tomography scan? So the patient goes inside this machine. And what is essential is that you get slices, maybe 1 millimeter apart, of the abdomen. And so on the lower left is you see the slices and the image corresponding to a slice. Okay, so we have these in these high resolution CT scans. And when we talk about the CT volume, this is a sequence of those slices. Okay, this is how the doctors see it. They have a program that displays the CT scans. They are recorded in what's called the DICOM format. And in this format, they can choose to view it axially. So this is like looking down, like from this way down, and frontally, as in the right-hand side. And then they can switch by choosing some options on the left-hand side. They can switch between different views, and also they can sort of highlight by playing with the contrast of the images. They can highlight different organs, because each organ here has a different grayscale. So if they want to analyze lungs, they choose the Akciğer or lung window. And if they want to look at the bones, they choose a different window, and so on. Okay. In fact, the CT scan has a lot more than the grayscale range. It's measured in what's called the Hounsfield units, so basically the radio density is measured with respect to the density of water and air. Okay, so air here has -1000 in these images. You have each pixel has -1000 or around that range of Hounsfield unit. Lungs may have this range. Water has 0. In bones, you get to the positives from 500 positive to around 1000 positive, and anything above is a metal in your body maybe will have a higher than 1000 or so Hounsfield unit. Okay, so these are very important to learn, and we have learned that from the Cerrahpaşa team in the beginning of the project through Zoom sessions. It was very rewarding for me because to be able to help doctors, to be able to help patients is really precious, and learning all about it in the meantime. So let's look a little more. So when we are talking about a CT scan, what we have here is on the right, going from the around the vocal cord area, on the right images. When we go down, we are going down, and you see that first the lungs start showing up as 2 little black circles because we see the top of the lungs, and then they get bigger and bigger and bigger as we sort of go down. And this is the axially cut chest image. And when you go all the way down, we are going further down. This is an infected lung image. And at some point, you see that the lungs are sort of getting out of the view where we are when we are approaching the diaphragm. Okay. So the problem then is, given the CT scan, which is the sequence of these slice images, would give us an estimate of the probability for the patient having the COVID-19 infection. To start with, Cerrahpaşa has collected a data set of roughly 100 healthy patients and 100 COVID-19 patients, and some of these people have more than one CT scan for repeat measurements. So all in all, we have 20 healthy CT and 31 infected CT, an average 260 or so slices in a CT scan itself. So the label is very important in supervised learning. This is how we train our neural networks, how we train our machine learning system in machine learning, deep learning in a supervised fashion. So what is the label here? So we have the patient level label here. So even though many of these images on the right-hand side do not even show the lung, or may show the lung, but may not show the infection, all of them right now are labeled as infected if they know that the patient is infected via the PCR test, for instance. Okay? So this is an example of a weakly labeled data. That is, it's not exactly true and it's not exactly pinpointing the right thing. So we are going to think about, how to deal with that. Okay, we can, as I said, we can still say we are feeding our network this and see how it comes up with, but we have other alternatives as well. So on average, only about 130, so about 50% of the slices in the CT scan are infected, even if the CT is labeled as infected. So this is something important to keep in mind. Okay, all right. So we can do how to approach this problem. We know that we are going to use deep learning. So we are going to take a neural network of some sort and we'll train it in a supervised fashion. But should we train the network with all images in the CT volume? This requires no segmentation at all. We have actually started with that, and we got something like 75% accuracy. And then we noticed that the more we learned through our Zoom session and WhatsApp messages and this whole interdisciplinary work between doctors and engineers and scientists. So we learned that we can actually use some simple segmentation techniques to find, let's look at number 2, to find at least the interval where the lung images even appear. So anything above the blue line here in the frontal view do not even contain images. So we should not mark those images as being infected. So those are just indistinguishable from healthy, thorax, the upper slice images. Okay, so then we switch to that, and we right now we can say that roughly the first 50 images in the beginning and the last 50 images in the end do not contain any lung issue. So we can actually say, if we want to, these are normal, healthy pictures, and the lung images are infected. Or some systems in the literature take the third approach, which is they actually go and segment the images so as to find the lung regions. And then they extract something like the white lung area on the right-hand side. And with the use of this mask, if you mask the original image with this mask, you'll only have the lung area with the remaining. Okay, so then we are actually looking in a more concentrated fashion where we want to look, okay? Then you can also combine this sort of like how to label, how to segment, they're sort of tied together. Do we give patient level label? Do we give slice level label? Or some systems, again, in the literature, they give region level label. They say, here's the data for you, it's infected and the infection is here. So they pinpoint the bounding box of the infection so that they can guide the neural network. Okay, so far we are trying, we are between 2 and 3, and 2 is better than 1. Okay, but this project is still ongoing, so we are gonna see how it goes. For segmentation, we basically use simple thresholding and simple mathematical morphology operations to find the mask, to find the lung areas, and then looking at the normalized lung pixel count, normalized by the number of body pixel count, so this being the body in the center. So you can find these intervals, and they do help in training the system. All right. So we have split our data set into training and test in an unbiased way, so that if a person has their CT, and if it's a repeated CT, so we don't put one in the training set and another in the test set. So we have a decent sized 80-20 ratio for the training test distribution. These are again some images from the healthy patients. They don't show as much of the variation of the lung shapes, but you see some of it. You can see them a little more here, where some organs start showing, and some of the infections I tried to highlight. They all have infections. The second one from the left also does, but okay. So as the approach, we have used deep learning, and we started doing this as, let's see first whether we can separate healthy versus infected tissue. We don't know if it's COVID-19 infected, but that's what the data is given to us. So it's either healthy or COVID-19. And we tried to learn it via what's called the transfer learning, using the Inception Resnet version 2, which is pre-trained. So what is this about? Well, maybe you all know, but I have to say it for the sake of everyone. So in transfer learning, what we do is assume we have a very, very, very large image set, such as the ImageNet, consisting of 1,000 object classes. And what we do is we'll take a network trained to do object classification over the ImageNet classes, and we'll use that trained system with almost everything remaining, all of the learned weights remaining constant, and just changing the last part. So if this was the network, and if this was the ImageNet on the right, ImageNet classes, what we do is we just erase the last set of weights. We learn them from scratch, the orange box. Let's say that we are doing gender identification or COVID healthy identification, whatever it is we just change the output layer. We will learn those weights corresponding to the output layer. Then we can slightly modify the yellow box area. So the weights in near the top layer, we can modify them, or we can just freeze them, meaning we won't change them, or we can just fine tune, just slightly change them. And the earlier layer, we just will freeze with the assumption that they are general purpose features that are already learned, and then will be also useful for our purpose. So if we are going to use transfer learning, of course, we are going to pick the most suitable, most similar domain, but the ImageNet seems to work pretty well for our task. Okay, So the ImageNet learns features like the, networks trained on the ImageNet dataset learns features like the top left portion shown here. And as you go right, as you go more and more, as you go deeper and deeper in the network, you see more and more complex features. Okay, so these last layers may be fine-tuned because your domain may be different. So in ImageNet, there are cats and cars and so on. In our current problem, we have just grayscale, healthy and infected lung tissue. So maybe we want to change them a little bit, but the assumption is that most of the information can be preserved via frozen weights. Okay. Okay. So in deep learning, what we have seen over the years is that in 2010, the error in this ImageNet competition was quite high, 28%. Then it was 25%. It was slowly improving every year. The year that AlexNet, one of these famous pre-trained networks, was participated in the competition, it was the winner with 16%. So there's a more than 9% point drop in the error. Okay, and ever since, there's actually more to this figure. Ever since, what we observe is that error rate is decreasing while the layers, the number of layers in the winning networks are increasing. So we have the famous AlexNet, VGGNet, GoogleNet, Resnet, and recently EfficientNet, CNet, and so on. Okay, another view. We are using the Inception Resnet version 2, which is a quite large network shown on the top of the slide here. It's a connection between Resnet and GoogleNet. So marrying the ideas of skip connections of residual network, Resnet, and the Inception modules of the GoogleNet. And this is sort of a more compressed view of the thing. So what we want to do is we want to give the one slice. So we are approaching this as if they are independent slices right now. This is just one approach. We are going to train a system that will look into one image and that will predict whether it's infected or healthy. And doing this, we are going to put together a system that looks at, right now, is looking at the number of slices that are deemed as infected. And if these are more than 20 or 50 out of 250, we call the patient as infected. Okay. If it's 1 or 2, maybe we'll say, oh, maybe it's just a fluke. It's an error of the system. Okay. And we learned that this is roughly enough. So minimum was sort of specified as 20 or so by the doctors. Okay. So we highlight the, as a pre-processing, we only highlight the right area of the DICOM format CT scans to see more of the lung areas. We also find, we are capable of doing the segmentation. We do some segmentation for the lung area to find at least the interval. And then when we train the network, we also use data augmentation. Data augmentation just says you have a network with millions of parameters that needs to be constrained in order not to overfit. So what we are doing here is a gentle data augmentation where we don't do much cropping, much rotation and so on, but we do it a little bit of that. So the idea is if you're looking at a face image or plant image, if you crop it a little bit, that shouldn't prevent you from identifying that plant or that the gender of the person or the person itself and so on. So data augmentation just refers to automatically generating variations of the input training data so that we can sort of increase our training data automatically so as to have more data that will constrain our system. These are our current results. We have an accuracy on image level of 94%, which corresponds to a best accuracy on patient level. So image level, we call this 90 infected or not, this slice, and this confusion matrix corresponds to that. But when you sort of put them together, if you have more than about 50 or so infected slices as predicted by the system, we call the patient as infected. With that, we have the best accuracy on the system at patient level, which is 96%. This is very good, but we have the false positive rate of 1, but false negative rate is also 1/31, okay? This is a little, so we played with the thresholds a little bit, and we are gonna look at the ROC curve as well. But if you use a slightly less threshold of 20, so if you have more than 20 infected slices, then we call the patient infected, then the accuracy falls a little bit. But what happens is we have no false negative. That is, we don't have any patient that the system misses. We do understand that these are still small numbers, but this is the very beginning of the project, really. The ROC curve sort of changes this threshold implicitly, any threshold, to vary the false positive rate versus the true positive rate. And we have such a curve, for instance, showing that around when the true positive rate is 95%, the false positive rate is less than 9% or so. Okay, so you catch most of the patients, except for the 5% part, and you unnecessarily alert the doctors in a small amount of the cases. So the operating point should be chosen, you know, by the comfort and convenience of the doctors. Okay. Finally, so with the deep learning, we like deep learning. It has brought a significant performance increase to many computer vision machine learning problems, but is it explainable? So there's some work regarding that. Can we visualize where the network is sort of looking, or, you know, what is basing its assumptions? So there has been some work regarding that, with sort of seeing which pixels, changing which pixels would change the decision of the system, or looking at the backpropagated gradient in the case of the GradCam, which what we are using is how the image, where the weights are sort of are affected by in this particular image. So when we are recognizing cat, it's here. When we are recognizing dog, it's here. And when we use this system, GradCam, on our problem, what we see is, yes, so the red is the most heavily weighting part. So indeed, the network learns to look at the bottom part of the lungs, where the infection is seen most, correctly. So this was also happy to observe. Okay, I'll skip these. In future work, what we are going to do is we are going to handle the problem as a 3-class problem first. So that is healthy COVID or other pneumonia-like patterns. So this will include cancer, cigarette smoking, and so on. And we are also going to, in the meantime, use more advanced deep networks. And another one is we are going to try models that will, without the use of a threshold, that will output the patient level decision. So we won't have to say, if there's more than 20 slices which are infected, let's call the patient infected. So what we are going to do is use the network to handle this. One way to do it is use a network where the input is the 256 slices themselves, and the output is directly the 3 classes that we are after. And here we have one advantage compared to fully flexible, input length. So we actually know this will be either 250 or roughly 500 or so, and we can actually even use sampling. So these are all going in their own path, and the different paths of the network share weights among themselves. So it's really the one path of weights sort of learning this problem, but doing it in parallel for all the 256. So here we can do more than, of course, what we have done with a simple threshold, okay? We can actually also look at the the central slices more importantly. So this is the talk about the COVID-19 detection from CT scans. I just put a few slides about the other projects from the VPA lab and Berrin, which is our Center of Excellence in Data Analytics. So we work on, so I just put the projects that this project team has worked on, and that also relates to this problem significantly. So we have been working on face attribute classification, so far with Sarah and now with Mehmet. So here the task is identifying facial features, both physical and behavioral, like smile, through one deep network. We have done several sort of nice improvements to a very competitive field of research. So one such idea is, can we use ensembles, which is shown to improve the performance of even deep networks? But it's, you need to train not just one, but maybe 5 or 10 deep networks, and they all take time. So in this idea, what we do is we actually make an ensemble within one network. And this has increased our performance significantly on this face attribute problem. And we have the state-of-art results for that. And another problem that we have worked on with Sarah is plant identification, skin cancer classification. These are all sort of where computer vision meets machine learning and sort of our interest areas, whatever we are interested in. And what we have learned in these problems do carry to this current problem, so they share some common elements. And finally, Umut will defend soon and what his work was, and again using deep learning, but in a more multimodal fashion. He has done deception detection. So in this data set, we look at videos of people on trials. These are real trial images, and we can recognize when a defendant is being deceptive, that is lying, by about 83% if you use a bit manual marking, or if it's fully automatic with 73% accuracy, which is quite a lot better than humans. Okay. That's it for now, so I'll take any questions that you may have.
Thank you very much, Berrin.
Yep.
So if anybody has any questions, please raise your hand and we can unmute you and you can ask your question.
You can also write it via the chat if you want.
In the meantime, I have one question,
Sure.
Quite practical. So imagine that we have your system up and running at Cerrahpaşa, and what would it take to put it in large hospitals? So what kind of infrastructure, and also from a human-computer interaction point of view, what would it take to make it easily user-friendly for medical personnel to use such a system, such a deep learning system? Because not only in medicine, in many other fields, this is one of the biggest problems right now. So you have all these beautiful algorithms, but then the real people who are going to use it, they don't have a clue.
Yeah, so this is a very good question. If it was just us, this would remain as a nice algorithm, nice system. So, but TÜBİTAK, UME, and Cerrahpaşa brought this as a collaborative project to our attention. And we have proposed this as a TÜBİTAK Binbir project with TÜBİTAK UME. So they are going to set up and test and evaluate and deploy this system to Cerrahpaşa. Probably won't take too much in terms of computing power. In fact, we propose to train and test in that system and just leave it there and as an up and running system. And in terms of the user interface, you're right. I think that we need to sort of, the way that we have shown those weights and so on, we need to give the doctor some view so that, the system, if it's erroneous, it doesn't take a long time. It doesn't cost more in terms of time than what it's worth. So it shows the slices that are marked as infected, maybe. It shows a confidence score and so on.
Okay, thank you. So if there are no any further questions, thank you very much, Berrin. And thank you very much for everybody there is one hand from Aykut Erdem. Okay, unmute.
Okay, thank you for the talk, Berrin Hocam. So I have just one question. Are there any differences between male and female patients? Did you also look at this?
The lung and the body, both the body shape is different. So you can actually, see the breast shape sort of, but otherwise I don't know. But the lung shapes and size changes. So if we want to do segmentation, we have to worry about that. But the lungs themselves within one CT show so much difference that, probably more than the male-female difference.
Okay, and I have just one comment, not a question, but there are some recent studies which show that these deep neural networks are indeed learning texture compared to like shape information. And in that sense, from your slides, I see that this might be a good fit to detect COVID, because like those broken glass patterns, they are more texture-like structures.
Exactly.
Thank you.
And actually, the early success sort of shows that this may be so, because it caught the texture immediately within a short duration of training. But we'll see how differentiable it is from other pneumonia patterns. Are you doing any work yourselves about health?
No, not yet.
It's quite rewarding, actually. Any other question?
There was one more hand, and then it disappeared.
All right. Erdener Hoca, do you have any questions?
There is one, yes. Emine.
Okay. Süpan?
Yeah.
It was mine, but you already answered, Berrin Hocam. Thank you very much. It was very informative. I was going to ask about the next step, how to train the network to differentiate the infection due to various types of infections due to bacteria or virus. But you already mentioned it, so thank you.
So they told us that, so when we said that we can do this in 2 months, they said, well, we were expecting this in 1 month. Couldn't we? And so we wanted to get ready, really, so do the fastest deployment if needed. It seems like we have some time now, so we'll take another month to polish it up and so on. All right. So I'll thank, Erdener Hoca, yes. Selim, can you unmute? I can't unmute.
Yes, I'm trying.
Okay. All right, Erdener Hoca, go on, please. I can't do unmute.
Yeah, okay.
Me right now?
Yes.
Yeah, okay. I'm Dr. Erdener Hoca. I'm a pathologist. I'm a medical diagnostician. I diagnose this disease based on morphological patterns under microscope. So, like in artificial intelligence, we conclude a diagnosis by looking at the patterns of the disease. I understand you're ambitious in diagnosing COVID-19 in radiological slides. It's a very excited area, especially very interesting in interdisciplinary research between medicine and engineering. And I think in the near future, artificial intelligence will be a complementary diagnostic tool for us. So it will be very beneficial, and I'm really excited to be in your session. And thank you very much. It was very great to be.
Thank you. Thank you. We are actually, as Berrin, we are going to have a workshop where we'll invite doctors and we'll invite scientists, computer scientists, and like electrical engineers and so on to Sabancı in our yearly workshop to sort of bring more such projects into life. Right. Atiye, do you still have a question? All right.
Okay, so thank you very much and have a nice afternoon. Goodbye.
All right. Thanks, everyone.